Yes, here we are once again. It's the physics video lecture. psci 168, video lecture 35. I'm going to start with some announcements today. I sent out an email about the portfolio assignment, the e-portfolio. And so I'll just say a couple words about that. These things always go out. I never actually see them, but I decided we're taking so many great notes that if you were just to submit a section of notes that you like, that's logical, well put together, nicely illustrated with some of the images that we've been downloading, then you can submit that to your GE portfolio. And I gave a little list of some topics. What was on there? Structures and hydropower, free fall and satellite orbits, that type of thing. But of course, you're free to choose something that you like. And then I said 4 to 15 pages. In our lab courses here in the physics department, we have our students submit one of the lab write-ups that they do, and that's usually between 4, 5, 6 pages lab write-up. So you'll have plenty of great material. I've seen some really nice notes, and so yeah, just do that, and that should be really good. So GE portfolio, that's all on you guys. I never see that. There's another thing that I wanted to briefly discuss, and that is your lecture notes, which at the end of the semester they comprise a book. Okay, so your notebook ordinarily I have people turn it in at the end of the semester, and I have a look at it and hand it back and give it a grade, give it some points. But what I want you to have in your notebook, you don't have to turn in all those notes to me, I've seen them week by week, but your notebook should have, when all is said and done, it should have numbered pages. So let's make a little list here. Numbered pages. And I'm responsible for the logic, and the whole course is very logical explication of all this physics that we've been doing. So you number your pages, and then you have a table of contents. And I'm thinking you guys will send me some images of your table of contents when you're done, maybe some random pictures. Okay, so you got that, and then an index. So at the end of your notebook, when all is said and done, you can have an index page, which is an alphabetical, just like an index in any book. An alphabetical list of names and vocabularies and concepts, whatever's important. Alphabetical list with the page numbers on it. And then you'll really have a useful object there. So that's our plan. I wasn't sure if I had mentioned that before this semester or not, but that's what we want to do. We want to have a numbered pages, a table of contents, and an index, and that'll be beautiful. Good, so much for that. Now what I want to do today is what I started last time, is to talk about wind energy. And I'm going to do this, I don't think this will take that long. I'm going to do an important calculation, and then I'm going to send you guys out to look up information and images again. Okay, that's the idea. So wind energy. Right, at this point in time, everybody's seen these gigantic towers with their huge turbines. Okay, there's a lopsided picture of one. You guys do better. Okay, so we got wind energy. Right, these things are standing up in the wind. These blades are as long as the wings on a jumbo jet. These things are enormous. And the question is, how much energy? And I said last time, first of all, okay, this lopsidedness too much even for me. How about that? Whatever. Okay. So how much energy? And the first point was that this is really based on heat transfer by convection. Okay, so wind is a convection current. Because, you know, we want to tie all these things together. And a convection current comes about because there's a temperature difference. And I was saying how the Earth is unevenly heated. Well, think about it on the very large scale. Here's the Earth rotating about its axis. Okay, the sunlight's coming in from here. And of course the polar regions just get a whole lot less sun than the equatorial regions. Okay. Because, you know, we talked earlier this semester, the sun is coming in, the sun is going to be much lower in the sky in the northern regions, and as such, it just projects less energy flux onto a surface. So you're definitely going to have uneven heating. You have it on a worldwide scale. Locally, you have it as well, just because there are mountains and valleys. And in time, you have it because there's day and night. Okay, so temperature differences, which give rise to wind, are ubiquitous. On the other hand, they're not always reliable. That's another question. So yeah, wind's a convection current. And this picture reminds us of uneven heating. But the uneven heating happens on many different scales. It happens on an entire scale of the Earth, and it happens locally. So my task right now is to answer this question about how much energy we can extract from moving air. And then your task, after I show that, is to go and find various resources that I'm going to outline. Yeah. So let's consider next. We have a moving mass of air. Okay, a moving mass of air. Well, we haven't talked about maybe we have. Have we talked about the density of air? Let's remind ourselves. Density of water, so density, I'll call it sub W, that is 1,000 kilograms per cubic meter. Well, the density of air also has some substance. Density of air, it's approximately 1.3 kilograms per cubic meter. Well, that's a whole lot less than 1,000, but still 1.3 kilograms is something. Okay. So what we're looking at is this mass of air flowing. Okay, a little wavy line, that's the wind. And what is it doing? It's going through a window. So if I were standing here and there's a wind coming at me, okay, there's a current, and I could put up a square meter. I could take this meter stick, put up a square meter, and then measure the air flowing through that square meter, like it's as though it were a window. So I put up a window here. There's my perspective, hope that works, through which air is flowing. And I'm going to give it some depth as well. Good luck with that perspective. We may have to start over, but there's an area here facing the wind. Out there, the wind's coming this way. So that's the perspective right there. Okay, so I'm saying how much energy, well, what kind of energy is it? We have a moving mass of air. moving mass of air, and so we've learned this semester we're talking about kinetic energy. So the next thing we have is kinetic energy of a moving mass of air. For example, if it were a moving mass of hot air compared to cold air, we'd say it had more thermal energy. But that's not what we're talking about now. We're just talking about this moving mass. You know, it's like a brick coming at us, except it's air. So kinetic energy of a moving mass of air, well, here we go. Capital K is 1/2 mv squared. Okay, we just write down the definition, how much we know. Okay, now there is this mass of air, but we're talking about this air coming through a window at us. So we have to modify this a little bit. Okay, let's give this a try here. Actually, I got a little more board. Maybe I can use what's under here. Okay, so we're going to modify this a bit. That's the kinetic energy of this. You know, you could say this is a cubic meter of air, and as it moves, that's its kinetic energy. But what about the energy of the air passing through? Okay, so what we're going to construct is an intensity. We're going to construct an intensity. I'll use the letter I. And remember, the dimensions of the intensity were watts per meter squared, which is the energy per time per meter squared. Okay, energy per time per meter squared. So we're going to take this 1/2 mv squared, and we're talking about the energy flux through this area here on the left. So let's take this bottom length of our cube to be delta L. Okay. So there's energy, and we're going to take delta L over delta T. Actually, let's do this a little bit different. We're going to end up at the intensity, but we're going to take it a couple steps in between. Okay, so we've got the energy, and then we're going to do energy per time. So power is equal to this kinetic energy over delta T, and power per area, which is our intensity, power per area, that's, let's get a nicer one here, that's kinetic energy over delta T, and the area in the denominator is delta L squared. Okay. Now I'm going to take this here multiplied by delta L over delta L, which is just a 1, right? So intensity is power per area, is energy per time per area, and I multiplied by 1, delta L over delta L. So let's see what we get now. I is equal to 1/2 mv squared, that's the K, I'm going to take a delta L over delta T, and that's going to leave me delta L cubed. Okay, delta L cubed. 1 over delta L cubed. Okay. So once again, I started with my energy of that moving mass of air per time. Okay. And then delta L per area. Now watch this. 1/2. Now I'm going to take this m divided by delta L cubed, put a bracket around there, and my delta L over delta T is a speed. Remember, distance over time. So I end up with v cubed. Okay. 1/2 m delta L cubed, v squared times v is v cubed. I'll write this out for you because v is equal to delta L over delta T, because if the wind is coming through this box, it's going the length delta L in the time delta T. Okay. So this is, do I have density? So remember, we have a density. So if we have a mass of air divided by a volume, that's a density of air. So what I've found is that I, which is the intensity, which is measured in watts per square meter, is going to be given by 1/2 density of air v cubed. That's a really simple formula, and we left nothing out. Okay, we've got air, this mass of air. Okay, but we're asking, you know, how much power per area when it flows through. So let's inspect this. Inspect this and see what we can do with it. Okay. The intensity. So this is intensity with the units watts per square meter. And remember, the solar constant had the units watts per square meter. So if I lay a square meter absorber here on the ground at noon, then remember I was getting 1,340 watts per square meter. And here I'm saying if I have a window square meter and air is rushing through it, that's how many watts per square meter I have right there. Make sure we put this in a box. I should actually rewrite it. Okay. This is our important result. Intensity. So I'm going to call it the wind intensity. 1/2 density of air v cubed. What else is there to say about this derivation? Could have been a little smoother, but this is what we have here. So once again, before we go to the analysis of this formula, we just had a mass of air, like this big box of air moving forward with speed v, kinetic energy 1/2 mv squared. Then the power per area, okay, is the kinetic energy per time that is passing by that boundary right there, okay, the blue part. The per area is the delta L squared. This was a little trick, you could say. Delta L over delta L. So I took this delta L over this delta T right there, 1 over L cubed, and then I took the 1 over L, that M over L cubed was my density in the square bracket. Delta L over delta T was a V, so I went from V squared to V cubed. Okay, let's see how we're doing time-wise. Oh, fantastic. So there's our wind intensity formula. and that's its derivation. So next, I'll use this side of the board here. We're going to do a numerical example. Well, I'm going to showcase this thing. So I'm going to erase this derivation. It's all there, and just put our formula up. Okay, so wind intensity. Now that we have that derivation, fair and square, energy intensity. So let's just write this here. 1/2 density of air V cubed. Okay. And underneath here, what we just had, the units are watts per square meter. And good to always remind us about the units. In this class, we're just always constructing things with kilograms, meters, and seconds. And so if we put numerical values in here, that's what the units will be, okay? Using kilograms, meters, seconds. Okay, two things to say about this wind intensity. The first thing has to do with how sensitive it is to the speed. So a cubic relation, so I proportional to V cubed. What does that mean? Suppose we had a speed we're going to calculate with 10 meters per second, okay? 10 cubed is 1,000. Nice. But suppose the wind speed drops from the initial speed to 1/2 the speed. Okay, 1/2 cubed is 1/8. So if the wind speed, which is say good and steady, drops to 1/2, and you'd say, well, 1/2 seems pretty good too. Nonetheless, you're going to drop from a certain value to 1/8 of the value. So this cubic dependence means that the wind resource is volatile. It changes not only between wind and no wind, but between certain wind speeds. So if V goes to 1/2 V, then I goes to 1/2 to the third I, which is I over 8. So that's, mathematically speaking, half the wind speed, 1/8 the power. So i.e. half the wind speed gives 1/8 of the power. On the other hand, double the wind speed will give 8 times the power. And twice the wind speed gives 8 times the power. Okay. So that simply is a mathematical consequence of this relation right here. Okay. And that cubic dependence. Something you have to know, right? So, and another point, so that's the first interesting point. The second one, I'm actually going to do numerical examples. And once I do that, I'll put up a list of some interesting things for us to find out. So the numerical example, and I have to make a little caveat here. You saw me derive this fair and square, okay, so there's nothing wrong with this formula. Nonetheless, the exact values that you get don't merely depend on this, because the fluid mechanics of air flowing past a body also get much more complicated. One way to see that is if you were to get all of the energy out of a flowing wind, it would mean that you had to bring the wind to a stop, and then you would get zero. Okay, so these, if you compare this with some stuff you're going to find out in the data out there, it will be very reasonable compared to this, but it won't be exact. Okay, and the reason why is if you were to get all of that energy, that would mean that you brought the wind to a stop. Okay, and that's not going to do it. Okay, so having said that, that's not really that important. I just want you to recognize that. In terms of the amount of energy to be harvested from a moving mass of air, it just modifies the 1/2, so to speak. Okay. Good. So, having said that, our numerical example, let V, this is quickly done, be 10 meters per second. What is that, about 25 miles per hour? Okay, so that's a decent breeze. So let V be 10 meters per second. And of course we said the density is approximately 1.3 kilograms per cubic meter. Then I is equal to 1/2 1.3 10 cubed. 1/2 times 1.3 times 10 cubed. So what do we get here? 0.65 times 1,000, so that's going to be 650 watts per square meter. Okay. Now 5 meters per second, 1/8 of that is going to be about 80. Okay. And 20 meters per second, 8 times that. Okay, so good. This will give you a good feel for energy to be had. So there's our numerical example, and now that you see how it's done, you can do them to your heart's content. The next thing is power from a large turbine. Okay, you want to do the power from a large turbine. And so here I'll draw the picture. These are the large turbine, and this thing sweeps out a circle of radius r. Now the power, just as it was with the sun, power is going to be the intensity times the area. Okay. So for this example, power is 650 watts per square meter. Yeah, what's that area? Well, area is pi radius squared. And now we have to ask, how big is this thing? Well, the really big ones, they are huge. Let me check my notes for just how big these things could be. Otherwise, I'll send you guys out and figure it out. See if I have these data. This is the kind of thing you can look up. I was going to go with 50 meter radius, but are they really that big? 50 meter diameter for sure. You know, I'm going to leave it on you guys. Let's go with let R equal 30 meters, 30 meters. These things are so big, there's probably one that big. Pi, so now 30 meters squared. Let's just see what kind of a number we get here. Okay. 3 times 650 is about 2,000, right? Pi is about 3, we're doing an approximation here. So 3 times 650 is about 2,000, so we're going to have 2 times 10 to the third times 3 squared. So we're doing approximation, so 30 squared is 900. So that's going to be about 1,000 as well, times 10 to the third. And that's going to be watts, okay, because we multiplied watts per meter squared times meter squared. Intensity times area. And good, so that is approximately 2 times 10 to the 6 watts. And yes, that's actually a good number for some of these large turbines. Okay, that would be 2 megawatts, 2 million watts at that speed. So yeah, go ahead and make sure we specify everything I've said here. First of all, power equals intensity times area. The area we're talking about swept out by the blades, so that's not that big window there. And this is for a 10 meters, this is for V equals 10 meters per second. Okay. Good, so that is actually the scale of what these large turbines can put out. Now I just want to write down a few things about what you guys should download and print out to make this presentation. I usually show a bunch of pictures on this, and there are wind maps and everything else. I'd like you guys to find those and include them in your presentation, in your notebook. So let's just call this homework for your notes, the way we've been doing it. So images of these turbines, first of all, of different sizes, right? There are smaller ones, but there are also giants. So you want to get some images of those with the sizes indicated, okay? With the sizes indicated. So that's the first thing. And while you're at it, you could probably get some images of the big wind farm installation where there are many of those, okay? So these sometimes, you know, you'll get an image of certain models that are stood up next to each other with the heights. And then so turbines on location, various, whatever you find that looks good. And the really important thing is, see if you can find a table of wind intensity. Find a table of wind intensities and compare the values they give with our formula. That'll, you know, you'll see they're right in the same range, but then you'll actually see, you know, you'll see it for yourself. You'll see for yourself how good that is. Table of wind intensity. And the fourth thing, if you can find wind maps. So there are maps, say, wind maps, there are maps that'll show where, that'll show the wind resource. There are places that are windier than others. And you'll see, for example, if you drive out to the Bay Area, or if you drive down south over to Tehachapi, there are certain passes where there's a good, strong, consistent wind, and then you'll see where these wind turbines have been set up. Okay, so you'll also see that on the wind map, or maybe we should call it a wind resource map. You'll find something. Okay. And of course, once you know the wattage and you know how it can fluctuate, then you can estimate, and of course a lot of this has been done, you can estimate how much is available from these things. So you got these different types of images, wind resource map. That will be good. So after this, we may do a bit of a review, but we have, you know, of all of our energy sources, because we pretty much nailed them all now, roughly speaking. Okay, we're not deeply into nuclear engineering or anything, but we do know that nuclear power couples to heat engines. Okay, now these turbines, they definitely need electrical transmission. So our last major section in this semester is going to be electricity and magnetism. It's going to tie everything together. Okay, but until then, until next time, have fun working on this, and we'll see you later.